सर्व विद्यार्थ्यांचे या केमिस्ट्री लेक्चरमध्ये स्वागत. टुडे students we are going to learn about next point 6.5 integrated rate law. So in this unit we see different points. First one, what is integrated law for the first order reactions in solution medium. Second one, units of rate constant for the first order reaction. Third one, half-life of the first order reactions, that is T half, and simply expression for the half-life and rate constant of the first order reactions. So just start with simply rate law. In previous lecture we see what is rate law. Simply at the rate of reaction at a given temperature and at a given time instant is directly proportional to the reactant concentrations. So for reaction A plus B, it gives C plus D. The rate law is rate is equal to K into concentration of A raised to X into B raised to X. That is X and Y, or X are the powers of that particular reactant concentration, which are raised to for simple powers. So what is the difference between rate law and integrated rate law? Generally, integrated rate law tells us the concentration of reactants for different times. Here the differential rate law, or generally rate law, are converted into integrated rate law. So what is the equation for the integrated rate law? We see a chemical reaction, that is you can see on your screen. A gives product. This is the simple chemical reaction. So we can write the differential rate law for this reaction. That is equation number 6.4. Rate is equal to minus D concentration of A upon dt is equal to K into concentration of A, where A is the, or in square bracket, A is the concentration of reactant at time t. Now we have to rearrange this equation. That is rate is equal to minus dA by dt is equal to K into A. As on rearranging, this equation becomes dA by concentration of A is equal to minus K into dt. So this is the equation number 6.5. Now consider A0 be the initial concentration of the reactant at time T is equal to 0, or at starting, and concentration of A at T is the concentration of A at time T, that is concentration A to the T. Now we have to put these values, that is of initial concentration of A and concentration at time T, in given equation 6.5. Concentration of A is equal to concentration of A0 at T is equal to 0, and concentration of A is equal to concentration of AT at T is equal to T, that is at a particular given instant time. Now the equation 6.5 is integrated between limits. These are the limits. We have to integrate equation number 6.5 between initial concentration and final concentration. So this equation become integration of dA by A from A0 to AT, that is limit, and is equal to K into integration of dt from 0 to T. So applying integration laws, that this above equation becomes ln of concentration A raised to A0 to AT is equal to minus KT from 0 to T. Substitution of limits gives, that is by solving this one, we obtain above equation ln AT minus ln A0 is equal to minus KT, or ln AT upon A0 is equal to minus KT. This is equation number 6.6. As we rearrange this equation, it becomes K is equal to 1 upon T ln A0 by AT. This equation is in the form of ln. We have to convert it into log form, or to the base 10, log to the base 10. We have to multiply it by 2.303. So the equation becomes K is equal to 2.303 upon T log to the base 10 concentration of A at 0 upon concentration of A at T, that is concentration or A0 upon AT. This is the equation number 6.7. Equation 6.6 gives the integrated rate law for the first order reactions. This is the equation for the integrated rate law for the first order reactions in solution medium. Now we can write this law in the form of equation number 6.6 is ln AT upon A0 is equal to minus KT. By taking antilog of both sides, we get AT upon A0 is equal to e raised to minus KT, or this equation becomes AT is equal to A0 into e raised to minus KT. This is equation number 6.8. This is also the another form of integrated rate law for the first order reaction in solution by applying some integration or mathematical operations. Now, third form of this equation, consider let A mole per cubic decimeter be the initial concentration of A at T is equal to 0. We have to consider the concentration of A at T is equal to 0 is equal to small a. And second one, let X mole per cubic decimeter be the concentration of A that decreases during time T. Now the concentration of A that remains unreacted at time T would be, that is, initial concentration minus the decreased concentration, that is X. Initial concentration, as we considered earlier, A, small a, and X is the concentration of A that decreases after time T. So the concentration of A that remains unreacted, here you should observe clearly, here concentration of A that remains unreacted at time T would be in bracket A minus X mole per cubic decimeter. Now substitution A0 and AT is A0, value of A0 and AT is equal to A minus X in given equation. Now equation becomes K is equal to 2.303 or 303 upon T log to the base 10. Concentration of A, as we consider, is small a, and concentration of A that remains unreacted at time T, it would be A minus X. So equation K is equal to 2.303 upon T log to the base 10 A upon A minus X. This is equation number 6.9. This is also equation for the integrated rate law for the first order reaction in solution. So we can write three equations. First one, K is equal to 2.303 upon T log to the base 10 A0 upon AT. This is the first equation, first form. Second form, AT is equal to, in exponent form, AT is equal to A0 into e raised to minus KT. This is the second form. And third, K is equal to 2.303 upon T log to the 10 A upon A minus X. These are the three forms or three equations which are represent the integrated rate law for the first order reaction. Now student, we see what are the units of rate constant for the first order reaction by considering the equation of integrated rate law, that is 6.7. So consider here integrated rate law is K is equal to 2.303 upon T log to the base 10 A0 upon AT. As log to the 10 to the base 10 A0 upon AT, it is unitless quantity, so we cannot consider here. The dimensions of K will be remaining will be T, that is time inverse. Therefore the units of K, that is rate constant, is second inverse, minute inverse, or hour inverse. This is the first point. Now student, we move the next point from this topic, that is half life of the first order reaction, that is T half. See on your screen. Simply, what is half life of the first order? The half life of the reaction is time required for the reactant concentration to fall one half of its initial value. That is, if we consider the initial concentration A, then the the time required for the concentration to fall is equal to A by 2. That particular time is called as half-life of the first order reactions. So half-life and the rate constant of the first order reaction, the particular equation for the half-life of the first order reaction. Now, as previously we see the equation for the integrated rate law for the first order reaction, equation number 6.7, that is K is equal to 2.303 upon T log to the base 10 A0 upon 80, where A0 simply it is the concentration of reactant at T is equal to 0 at starting. Now it falls to 80 at a time of T after the start of the reaction. Reaction starts, then after some time, that is at a particular time T, it becomes 80. The time required for A0 to become A0 by T, that is half-life. Simply initial concentration A0 and its half is A0 by 2. It is denoted by T half. Simply AT is equal to, that is at a particular time T, AT is becomes, or it is equal to A0 by 2 at T is equal to T half, that is half-life of the first order reaction. Now we have to put these values of AT and T in above equation, that is K is equal to 2.303 upon T log to the base 10 A0 by 80. So this equation become K is equal to 2.303 upon T half, that is we put the value of T is equal to T half, half-life or time, log to the base 10 A0 upon A0 by 2, that is value of AT is equal to A0 by 2, that is the concentration of initial concentration, and time required for the to become it is half, that is A0 by 2. Now we have to consider or solve this equation 2.303 upon T half log to the 2, as it is in denominator, it comes in numerator 2, and A0 gets here cancelled. So next step is 2.303 upon T half is equal to 0.3010, that is log of the 2 to the base 10. Now we have to multiply 2.303 into 0.3010, it becomes 0.693. So equation becomes K is equal to 0.693 upon T half, that is we have to rearrange the equation, shift T half to the left and K to the right side. So equation becomes T half is equal to 0.693 upon K. So you have to correct some terms from this expression. There are some printing mistakes here. First one is, that is equation by after putting the values of AT and T, that is equation K is equal to 2.303 upon T half log to the base 10 A0 upon A0 by 2. Here only single A's concentration of A in bracket it is given. You have to correct the it is concentration of A at time T is equal to 0, that is A0. And second one, last equation number 6.10, T half is equal to 0.693 upon K. Here printing mistake, K half, not K half, only K. That is the last equation for half-life, and the rate constant for of the first order reaction is T half is equal to 0.693 upon K. This equation shows that the half-life of the first order reaction is independent of initial reactant concentration, and this is shown in your graph. That is here figure or graph is plot of AT, concentration of A at time T versus time T, and this is the graph or equation. This shows the half-life and rate or relation between half-life and the rate constant or the first order reaction. That is the half-life of the first order reaction is independent of initial reactant concentration. So students, in this lecture we see the next point, integrated rate law. That is the rate law, integrated rate law. It is particularly tells about the concentration of reactants for different times. So next one, expression for 8. That is, there is three forms. First one, k is equal to 2.303 upon 10 log of a0 by 80 at the to the base 10. This is the first form. Second one, in the exponent form, 80 is equal to a0 into e raised to minus kt, and third form, k is equal to 2.303 upon 10 log to the base 10 a upon a minus x. These are the three forms of integrated rate law for the first order reactions in solution medium. Now units, particularly considering equation 6.7, the unit for rate constant is equal to second inverse, infinity inverse, or h inverse, that is our inverse. Now next one, what is half-life? Particularly half-life, there is time required for the reactant concentration to fall to 1/2 of its initial value or initial concentration. Next one, expression for half-life, and the rate constant of the first order reaction is T half is equal to 0.693 upon k, and the graph for the this half-life of the first order reaction, that which shows the half-life of the first order reaction is independent of initial reactant concentration. So thank you all students for joining this